what you're supposed to worry about is probably the most beautiful piece of code you're ever going to see in your life, which is tree map. And to show you what it does, I'm going to say tree map square T1. And it gives me another tree like this, where each datum is the square of the corresponding datum in T1. So it's a tree with the same shape as T1, and I've applied a function to every datum in the tree, not to every node, because a node is the datum plus the children, but to every datum, the things at the nodes in the picture. And I get back something that's the same shape as the input, no matter how complicated the input tree may be, applying a certain function to each datum in order to get the result. And we do that with 4 lines of scheme. And I hope you realize how impressive this is because of the fact that this is a complicated data structure. You have to kind of wend your way through it and look at all the children, and don't forget the datum of the node you're at, and so on. And this little program does all that. How does it do it? Well, what data type, first of all, should the result of calling tree map on a function in a tree be? What do you get back? A tree. How do we make trees? We use the constructor makeTree. Now, makeTree takes 2 arguments. The first one is a datum. So what datum should we put at this node we're constructing? And for that, we just apply fun, the argument function, to datum of tree. Okay, everybody clear how that makes sense? We're given a datum and children. We call square, in this example, on each datum. So now we have to say, what should the children be? Well, the result of calling tree map on, let's say, this node right here is this node right here. Okay? And in general, in the result, we're going to have one child in the result for each child we have in the original, right? And what is it that we do to those children? Well, we tree map them, because each node is a tree, right? So what we want to say, basically, is map, tree map, children of tree. We can't quite say that, because tree map is a 2-argument function. So I have to say instead map, lambda of child, tree map fun child over children of tree. And that's it. Wow. Was that easy? Where's the base case? Say it louder. In the map. Yes, buried inside of map is, if this is an empty list, then just return the empty list. Do you have a question? That was your question, okay. So what's going on here, if you think about it hard, is actually pretty complicated. When is children of tree, when is the argument to map going to be empty? Well, 2 cases. One is children of tree is empty. What kind of a node are we at? If children of tree is empty. Your choices are root, branch, and leaf. Leaf, we're at a leaf node. So that's a kind of vertical base case. We've gone as far down as we can go. When else is map going to be called with an empty list? Besides being at a leaf node. All right. Let's say we're doing tree map of this node here, the one that starts with 5. And direct your attention to the children of 5. Even for a leaf node, this is not just a 6. It's a node whose datum is 6 and whose children is the empty list. Okay? But what we have is a list of 3 nodes. So map is given this list of 3 nodes, and it cutters its way down the list until finally it runs out. Okay? So one base case is the sort of vertical end of things when we're at a leaf node, and the other is a kind of horizontal end of things when we've run out of siblings. Right? Neither of which is explicit in this code, because map just takes care of it. And we're leveraging the abstraction of a linear sequential list to help us build the abstraction of a two-dimensional hierarchical tree. Okay? You are not going to totally get this piece of code sitting here in the room today. You're going to go home and take it home and stare at it for hours and play with it and poke around inside it and trace the calls to map until you finally get it. But you will see that these 4 lines here are like the most beautiful thing in the universe. Just an amazing thing that we can do that. And it's not, by the way, that I got to write this beautiful thing because I'm brilliant. It falls out of the nature of abstract data types. Yeah. So what would, the running time? Basically, you have to look at each node, at each datum, right? So it's linear in the size of the tree. Unlike the case with the binary search tree, where we could avoid looking at some of the data. And so it's only proportional to the depth of the tree rather than to the total number of items. But here, we have to look at every item. Okay, so a two-dimensional data structure gives rise to a kind of two-dimensional control structure as you're tracing out what's going on here. You're going to start with a node, and you're going to look through its children and go left to right in the children, but within each child, you're going to go top to bottom. So what's the order in which the computer actually figures out squares of numbers? Well, it depends on the order in which STK chooses to evaluate arguments. The scheme standard does not say the leftmost argument has to be evaluated first. That's left up to the implementation. Some go right to left. I don't know of any that do something other than left to right or right to left, but it's imaginable that they might do the easy ones first or something. So we don't really know, but let's say it goes left to right. In that case, first we square 1, then we square 2, then we square 3, then we square 4, then we square 5, then we square 6, then we square 7, then we square 8. So that's the order in which things actually happen. So it's 1, 2, 3, hit a base case, back up to 2, down to 4, hit a base case, back up to 2, hit a base case for running out of children, back up to 1, down to 5. Right? That's how it goes. And all of that incredibly complicated up and down, left and right structure is in this call to map that calls tree map, but it's not tree map calling tree map, it's map calling tree map. Right? So I mentioned last time the idea of mutual recursion. And what we have here is a mutual recursion where tree map calls map, and map calls tree map more than once. Map calls tree map as many times as this node has children. Okay, whichever node we're looking at. So that's what gives rise to the two-dimensional control structure, is the mutual recursion. Yeah. Can we do it without mutual recursion? Yes, but you're not going to like it, the answer. Anything, it turns out, can be done iteratively, just, with one tail call. But the cost of doing that is that you have to build explicitly yourself a data structure full of unfinished tasks. So in essence, you have to write a little scheme interpreter on your own that remembers what parts of this problem it hasn't solved yet and goes through them systematically. So you really are doing the equivalent of a mutual recursion, but you're doing it in a more complicated way. But it is, it's iterative. So that used to be, as I said, that used to be really, really important in the days when computer memory was expensive and small. People were happy to find iterative equivalents to recursive programs. Today, if you're dealing with a two-dimensional data structure, please don't try to do it iteratively. Okay? Mutual recursion is your friend. Enjoy it. It lets you write tiny little programs like TreeMap. Other questions? Yeah. Say it again. Yeah, if you're doing something in two dimensions, you should naturally think about mutual recursion, yes. And in particular, you should think about this trick of using map to handle one of the dimensions for you. Okay? The vertical moves are sort of handled by this call to children right here, which is outside of the map. But inside of map is where we deal with horizontal motion across siblings. Okay, great.